Hello everyone, myself Rajeev Singh and I'm a physics faculty. So once again I am with you with Doppler effect, right? So today we are going to study what is the Doppler effect. But before that we have to learn how to measure frequency of sound, how to measure frequency of light. But in this case we will discuss only Doppler effect in sound. So first of all, we will try to measure frequency of sound, right? So see here how to we can measure frequency of sound. So we are going to start here. Frequency, how to measure, how to measure frequency of sound, right? How to measure frequency of sound. Okay, fine. So see here. Suppose that this is a point of source. Suppose that this is a point of source, right? And on the same line, suppose that here observer is standing. So from here what happens? Sound will release, and this sound reaches to the observer. Let a speed of sound, let a speed of sound is c. Basically, generally we are taking a speed of light c, but here we are taking a speed of sound is c. So what happens? Sound will go from here to there in the form of wave, right? In the form of wave, they will go from here pulse. You can say, if I'll take the line here, so sound from here to there go like this, right? So how many pulses? Lot of pulse. But the thing is that how many pulse, how many frequency it will heard in 1 second. So I'm writing here number of wave, number of wave observed by observer, observed by observer in 1 second, number of wave observed by observer in 1 second is equal to frequency. Like here I modified the definition of frequency. Generally we know that definition of frequency means number of disturbance per second, or you can say number of wave or number of cycles per second is called frequency. Same here. Why I take here number of wave? Because we know that in one cycle how many wave? One wave. So same previous definition was also the same. Previous definition is what? Number of frequency cycles per second. So number of wave means number of cycle ultimately. Getting my points? Okay. Now the thing is that if this, how we can find number of wave, right? So this is the one point. Number of frequency is equal to number of wave in 1 second. Now the thing is that how we can find number of waves, right? So number of waves is equal to distance by wavelength. Distance by wavelength. Getting my points? Distance by wavelength. So just see, suppose that sound is going from here to there like this. Sound is going from here to there like this, and this distance is d, I assume, and its wavelength is lambda. if anybody asking to you how many number of wave will be in this distance d, how many wave will be there, so we can write d by lambda naught will be number of wave, and this number of wave in 1 second is called, wave frequency. Getting my point? So this is the method to measure frequency of sound. I think up to here it is completed how to measure the frequency of sound. Proceed to the next page. See, suppose that I'm taking the first case, okay, but think here. Before that, I would like to introduce something. Now coming the thing, what is the Doppler effect? You understand how to measure the frequency of sound, because this will be help us to find the formula. We will see in upcoming case. Now what is the Doppler effect? So before that, I would like to introduce something. Suppose that this is a line, this is a straight line, and on this straight line, this is the source of sound, and here one observer present. So suppose that this source is moving with velocity vs, right, towards the observer. It is at rest. So tell me, when the source will come towards the observer, frequency of sound will increase or decrease? Suppose that its original frequency is f0. When source will come towards the observer, it is our real experience. In real life we have experienced this thing. Whenever the vehicle coming towards us, the horn frequency increases. Yes or no? We have felt this one in real life. Everyone feel this thing. So we can say this appeared frequency must be greater than real frequency. Same, in the same case, if the source, suppose that this is a source, if the source going away from the observer, then what happens? Appeared frequency will be less than f0. This thing is also we have experienced in our daily life. Everybody experience this thing in their daily life, not from one day, 2 day, even from the creature of earth. Whenever earth created, from that day, everyone experienced this thing, but no one noticed like this. Just like Newton's law. Why? Newton's think why apple fall down? Why not go up? Right? Similarly, this phenomena happening from the last many years, but only one scientist there, Doppler, he noticed about it. Only one scientist there, Doppler, he noticed about it and find the reason behind this. Because of that, this is called Doppler effect. Up to here completed. What was the Doppler effect? Basically, whenever sound coming towards the observer, frequency of sound increases. Whenever sound coming towards going away from the observer, frequency decreases. This is not a new phenomena. This is a very old phenomena, and this was happening from the creature of earth. But this was only observed by Doppler and cause find behind it by Doppler, so that it is called Doppler effect. Right? Now coming on the definition of Doppler effect. What is the definition of Doppler effect? See. Whenever there is relative motion, between source and source of sound, because we are discussing here only Doppler effect of sound. Source of sound and observer, and an observer, whenever there is relative motion between source of sound and observer, then appeared frequency appeared frequency will be differ than will be differ than real frequency, real frequency, and this was real frequency, right? And this phenomena observed by Doppler, can I write here? Yes. And this phenomena explained by Doppler so that it is called Doppler effect. So I think it is clear to all of you, whenever there is a relative motion, yeah, this is an important point. I will explain you why this is a relative motion. I will explain you whenever I will take lot of cases, then I will explain you, so be sure. But the definition is that whenever there is a relative motion between the source and sound and observer, the appeared frequency will be different than the real frequency, and this phenomena explained by Doppler, so that it is called Doppler effect, right? Now coming one by one on the cases of Doppler effects, right? Okay, till now if anybody have any problem, you can comment. So case first, when source and observer at rest, when source and observer at rest, stay, right? So take this point. Suppose that this is a line. On this line here, source of sound, and here observer, right? This is an observer. Take another pen here. So from this point, I will take sound is going. Sound is going like this, right? Okay, fine. So we have to calculate frequency. I assume its real frequency is n naught and real wavelength is lambda naught and a speed of sound is c. I assumed, right? Okay, so the thing is that how we can measure the frequency observed by observer. So I have already told you the number of wave travel in 1 second, or simply you can say the number of wave in a distance of 1 second. So the thing is that how much distance part sound will travel in 1 second. So we know that distance travel see, distance travel by sound in 1 second is equal to what? C into 1. It means D is equal to become C. So we know that frequency is equal to number of wave in the given distance. We know that frequency is equal to number of wave in the given distance. So number of wave will be number of wave is equal to, we know that, lambda by C naught, or that is also called frequency, and this will be C. D is what? C lambda. Okay, how we can find lambda? So we know that wavelength is equal to speed by frequency. So if I will put this one here, so this will be n naught, get cancelled. So number of wave, it means absorbed frequency or appeared frequency. So appeared frequency is equal to n naught, and n naught is what? Real frequency. So this is a real frequency. So what we can say, whenever there is a no relative motion between source and observer, it means both are at rest. Both are at rest. In that case, if both are at rest, in that case, frequency absorbed by observer will be real frequency. It means no change in frequency. If anybody asking to you what is a change in frequency, so that will be 0. What is a change in wavelength? This will be also 0. I think it is completed. Yes. Okay. Take the another case, that sub case. This is not another case. This is a sub case of case first. Or simple, you can say, take one example. Suppose that this is a source of sound. This is a source of sound. Okay, fine. And here one observer. Suppose that this source moving with 3 meter per second and this one also moving with 3 meter per second, right? Okay. Suppose that its frequency is 3 hertz. The thing is that what will be frequency absorbed by observer? So see what I told, whenever there is a relative motion, then frequency will exist. Frequency will change. But here both have same speed, 3 and 3 in the same direction. So relative motion is what? 0. So what we can say, there is no relative motion. There is no relative motion. Right? So that there is no relative motion, so that change in frequency, I can write here, change in frequency delta F will be 0. To change the frequency, there must be relative motion. The thing is that what is the need of relative motion? Why it will change? See, I think if it will move 3 meter, after 1 second it will be where? Suppose that right now, I will explain why we need relative motion. Suppose that right now this distance is 10 meter. I take another pen. This distance is 10 meter. Okay, suppose I am going to take the pen. Okay, suppose that this distance is 10 meter. Which distance? From here to there. From here to there, this distance is 10 meter. Okay. And how many wave here? And here I assume 6 or 5 wave, doesn't matter. You can assume anything. How many wave complete? 1 wave, 2 wave, 3 wave, 3.5 wave, right? So wavelength will be what? Lambda naught will be, we know that I told you. Yeah, you can see number of wave given here. So if number of wave given, so lambda naught you can calculate, because you know, just hold. Okay, fine. See, you know, number of wave n is equal to dy lambda naught. So lambda naught is equal to what? Dy n. What is the d here? 10. And number of wave, this is the n. So n is also, we absorb 3.5, it means 7 by 2. So this become 20 by 7. Fine. Okay. This is the initial. Now think after 1 second. After 1 second. Because this is a initial. So after 1 second. After 1 second. What happened? I again going to explain one by one. Initially source is here. Right, initially at t is equal to 0. After 1 second, source will be here. Because we know that source will travel distance 3 meter in 1 second. 3 meter. Initially observer was here, but right now observer is here. So observer also move how much distance? 3 meter. So see, what is the distance between again observer and source, or you can say source and observer? Initially this distance from here to there 10 meter. Now asking what is the distance from here to there? Again 10 meter. Why? Because it moves right 10 meter, it will also move right 10 meter, right? So again what will be lambda? Go and see what will be lambda. Same wave number will exist. So again lambda will be 10 by 7 by 2, because same wave number, source will release the same wave. So again there will be 7 3.5 wave like that, right? So lambda will be 20 by 7. So what happened? This lambda is equal to what? Lambda naught. So we know that frequency is equal to c by lambda. So simple, c by lambda naught, and it means original frequency. So see, if there is a relative motion, so distance between source and observer will change. If there is a relative motion, so distance between source and observer will change. It means the division or distribution of wave is also get changed. If distance decreases, so it will compressed, right? It will compressed. If distance increases, there will be rarefaction. Distance increases, the wavelength decreases. Simple, you can take this example with another way. Suppose that you and one of your friend, you both have 100 rupees, right? You both have 100 rupees, right? And no, think, you have 100 rupees and your friend has 50 rupees. How much you have? I going to explain. 100 rupees and your friend has 50 rupees. What is the change? This change will be 50 rupees, right? Okay, fine. Suppose that this money increases by 10. This money increases by 10. This money will also increase by 10. So right now change will be 50. But suppose that this money increases by 20 and this money increases by 10. What will be difference? 60, right? Same here happening. If distance between the observer and source decreases, wavelength increases. Wavelength increases. If distance between source and observer increases, wavelength decreases, right? If they both have same speed, it means distance between them will be fixed. So there is no change in wavelength. So that their need of relative motion, right? Okay. So this was the case first. Now coming on the case second. Don't worry, I will take example one by one also. First of all, I want to finish cases, then I will take example. See here, case 2. When source is moving, right towards the observer with Vs. I assume velocity of source is Vs. So take its diagram. It is a very quite easy. You can find in easy way formula. See here. The basic formula I will use. Whatever formula I have used, I have explained you in the recently previous section. Only this formula we will use here, right? So this is at rest, and this is moving with some speed Vs. Fine. Okay. So you have to think. Suppose that uh, sound is going from here to there, right? Suppose that sound is going from here to there. Fine. Okay. So suppose that sound, what will be, suppose, right, what I'm telling you, if this sound from here it is released, right? Take another pen. This sound released here, and this sound reaches to this point. When this reaches here, at that time what happened? This source will also move some distance. This source also will move some distance. It means, what is the real distance traveled by sound? This will be real distance traveled by sound. Try to understand. Suppose that the source will release this first sound, first wave. So this wave reaches here. At the same time, source will also move from here to some other place. Suppose source will come here. So what is the actual distance moved by sound? Only sound will move this distance, right? So what we can say, suppose that they taken time t, they taken this sound will take from here to there time t. So this total distance become c into t. This total distance becomes c into t, because I assume sound take the time from here to there t second. Okay. So what will be this distance? Can you say? What will be this distance? Because source will also travel some distance. So this distance become Vs into t, because the speed of sound is Vs, source Vs into t, this distance. So what is the actual distance traveled by sound? This is the actual distance traveled by sound y. So I have to calculate distance y. Fine. So if I will use here c, so y will be what? Y is equal to will be ct minus vs into t, right? Ct minus vs into t. Now we know that number of wavelength is equal to distance traveled by sound in 1 second divided wavelength. Number of wavelength is what? Distance traveled in 1 second divided wavelength, right? So first of all, find distance traveled in 1 second. So from here we can say distance by sound in 1 second. So from here, if we will find a small d, this will be c into 1, time is will be 1, minus vs into 1. So this become what? C minus vs. So number of wavelength, right? Number of wave you can find, or simply you can find lambda first of all. So what will be lambda from here? So from here, if you will going to calculate lambda naught, lambda dash, you can calculate also. So lambda dash will be what? Just hold. From here to here, how many wave will be there? From here to there, lot of wave will be there, so I have to calculate first of all number of wave. So number of wave, we know that okay, here lambda also will change, right? So first of all we need to calculate lambda. Okay, fine, no issue. And then number of wave, just hold 1 minute. Where is this point? So yeah, you can see here, this is a C minus Vs. It means particle or wave will travel only this distance in 1 second, right? This is C minus Vs. It means I can say in another way, just see here, suppose that this is a sound and sound going like this. So this is what its wavelength, right? But source is not static. When this sound will reach here, in till that, till time, or till, or you can say at that time, source will be here. So what is the effective wavelength of sound? This will be effective wavelength of sound, lambda effective. So lambda effective will be from here, in from here to here. Suppose it take 1 second. So what distance it will travel? C, and sound will travel. Here we have already calculated minus Vs. So lambda effective will be C minus Vs by n, right? C minus Vs by n, because a speed of here sound becomes, you know, I told sir, a speed of sound, because distance travel in 1 second is also called a speed, because we know that distance is equal to a speed into time. So in 1 second this is a speed. So a speed of sound becomes C minus Vs. So lambda effective becomes, or lambda apparent you can also say, lambda apparent you can also say, this become C minus Vs by n. So now we have to calculate number of wavelengths, right? So see, frequency is equal to, we know that frequency is equal to, we know that a speed of sound divided lambda apparent. So this become C by C minus Vs by n. So from here this is a apparent frequency, and this will be C by C minus Vs into n. N naught you can say also, this is the original frequency. So this is a formula to calculate apparent frequency when source is moving towards the observer. So you can see when this will increase, this whole quantity will decrease. If this will increase, this whole quantity decrease, denominator will decrease, it means resultant will increase, right? Because of that, whenever a vehicle is coming towards us, we are getting more frequency horn as compared to when vehicle going away from the us. Take sub case. It is a part of second case also. See, again, suppose that this is a source, but right now this source is going in this direction with velocity vs, right? And here observer, he is at rest, or it is at rest. So you have to think here. Suppose that right now at t is equal to 0, this is basically our source. Sound is going from here, right? Okay. At t is equal to 0, wave is going like this. From here wave released, and this wave is going like this. Okay, I'm not going to make the proper waveform, just for your understanding I did this. Okay, after 1 second what happened? At t is equal to 1 second. What happened? After 1 second, this source will go away from some point, or you can say this source will be at some other point. This source may be, right, this is here. After 1 second, this source will be here. Try to understand why. Because source is moving in condition. Okay, now wave is going from here. Initially it is here. So what is its distance? This distance will be after 1 second, this will travel distance vs. Getting my points? So now what we can say, this source, this sound is not coming from here, this sound is coming from here. Well, now what we can say, this sound is, just erase this one. Now we can say this sound is coming from here and it is going to observer. So this sound is coming from here like this, right? So basically this is supposed that initially C, I assume this is initially C. So right now this will be, suppose that whatever you can assume this is a Vs, so this will be effective distance travel by sound in 1 second. Getting my points? Effective distance travel by sound in 1 second. So now Y will be, in the previous case we have taken Y is C minus something, but here Y will be C plus Vs. C plus Vs. Okay, so we can again calculate lambda apparent. What? Okay, this is also a speed of sound. A speed of sound also. A speed of sound. Not real speed, apparent speed, right? So this become C plus Vs by n. C plus Vs by n, this become lambda apparent. So frequency apparent is equal to, we know that a speed of, real speed of sound, frequency of wavelength is equal to real frequency of sound divided apparent wavelength, sorry, real speed of light divided apparent wavelength, C plus Vs by n. So this result become n naught times C by C plus Vs. So this point you have to keep in your mind when observer coming towards the, when source coming towards the observer. In that case, this become C minus Vs and away from C plus Vs. We can take another case. Case third, or you can say case, yeah, I think case third. Okay, hold. Right, when source we have already discussed. Okay, source is at rest and observer going towards source, observer going towards source, okay, fine. See here, so what we can say, suppose that, take another pen here. Okay, suppose that this is a source and this is a observer, right? But source is at rest. So what happened? Sound, take another pen once again. sorry, see. So see, sound release from here. When suppose that when they're meeting here, right? Or simply you can say, what will be distance travel in 1 second by sound, right? So see, if sound will travel in 1 second, how much distance sound will travel in 1 second? C distance. Suppose that it will travel C distance, and this will also travel some distance, so they both will meet here, right? Both will meet here, suppose that. So total distance becomes C plus V. Suppose that speed of observer is V naught, so total distance will travel with the V naught. Getting my points? If think observer is at rest, so what we can say, the sound will go to the observer and reaches here. What we can say, basically sound and observer, take another pen, sound and observer will meet here. But if we take at rest, it means what happens, sound will go from here to there. It means in 1 second how much distance sound have traveled? In 1 second they have traveled C plus V naught distance. Getting my point? Just simply you can say, in 1 second sound will move C distance and observer will move V naught distance, but observer will say no, I am at rest. It means sound will travel C plus V naught speed. So what we can say, distance travel, say distance travel by sound in 1 second, right, with respect to observer, this will be C plus V naught, and this is a basically apparent speed of sound. This is the apparent speed of sound also, because distance travel in 1 second is called also a speed. So lambda apparent will be, my dear, lambda apparent will be apparent speed divided its frequency in naught, right? Now apparent frequency will be C by lambda apparent. So this will be C by क्यों मम्मी पानी तो पी रहे इसी पूरा बोतल भर के लिए रह दो पी दे हाँ ठीक है. So lambda apparent will be, my dear students, from here you can see we doing some mistake. Lambda apparent okay, some mistake is going here. C by lambda apparent, so here, or simply you can say na total distance is what, C. So this will be lambda apparent हमारे पास हो जाएगा C plus Bs by n naught. Some mistake is going there. Distance travels, number of wavelength you can find from here. If you find the number of wavelength, so this number of wavelength will be lambda naught if you divide. So lambda naught will be C by n. Okay, done mistake going here. One thing. Sorry, some mistake there. So what we can say, this become C plus Vs, sorry, V naught. So we know that number of wave, right? Number of waves is equal to what? Distance by lambda naught. So this becomes C plus V naught by C by N naught. So this is also called frequency. I have explained in the first slide how to measure frequency. So apparent frequency will be N naught into C plus V naught by C, and every time I'm telling you N naught is the real frequency, C is the speed of sound, and V naught is the speed of observer. In the same case, if we will take another part, suppose that case number 4, case 4 I think, or case 5, whatever you can just remember. Now when observer moving, right, moving away from source, when observer moving away from source, so just take its diagrammatical representation, then we will start, right? Okay, fine. So see here, I forget to plug the mic. So when observer moving away from the source, so just see here, this is a source, and from here sound is releasing like this, right? Okay, and here observer. So suppose that in 1 second sound will reach here. Suppose that in 1 second sound will reach here. So 1 second, how much distance sound will reach? C distance sound will reach. In that 1 second this observer will also reach. So this observer will reach this distance V0. Again you have to understand here what? Suppose that in 1 second this sound, just hold, take another pen. Suppose that in 1 second this sound from here and reaches to here. So in that 1 second, how much distance will observer will move? This observer will move this distance V0. So what is the effective distance traveled by sound? So this becomes C minus V0. This is the effective distance traveled by sound in 1 second, right? So number of waves, that's wave number or frequency, is equal to C minus V0 by lambda naught. So this will be lambda naught, you know, C minus V0 by C by N naught. So this will be, my dear, N naught times C minus V0 by C. So this will be our apparent frequency. This will be our apparent frequency. So F apparent, from here see, F apparent will be N naught time C minus V naught by C. So we have observed from here the apparent frequency in all cases when source is moving towards the observer moving towards the source. In all these cases this is, if you will summarize all 4 cases, so see, first case, right, first case what? N apparent or frequency apparent is equal to original frequency, because in first case no one was moving, right, all are at rest. In second case we got a thing, source was moving. In second case we got a thing, what? Source was moving towards the observer. In that case apparent frequency is equal to N naught into C by C minus Vs. Okay, in the third case we got it, apparent frequency is equal to N naught by C plus Vs, right? And fourth case we have observed apparent frequency is equal to N naught into C plus V naught by C. Fifth case F apparent is equal to, here we have calculated N naught into C minus Vs by C. This all formula we can be remembered by using short trick. See, this all formula we can remember by using short trick, or you can say short formula. Please look here everybody, short formula. F apparent is equal to always N naught into relative speed of sound. Please look here, relative speed of sound with respect to observer divided relative speed of sound with respect to source, right? This formula you have to remember only for all the 5 cases. Only this formula you have to remember. I'm going to verify this formula one by one. Same result we will get here, right? So just check it. What was the first case? So first case, both are at rest, right? If you will take the first case, I'm just going to check. First case was both are at rest, Vs is equal to 0, V0 is equal to 0. Put here. What the apparent frequency? Apparent frequency is equal to N0, right? What will be relative speed? Relative speed always will be here. This will be C plus minus V0 by C plus minus Vs. Here you can also make one more formula. We know that relative speed always either subtract or add. So in this case, this formula will be C plus minus V0 divided C plus minus Vs. Simply you can take from your practical and all the derivations. Either see here, if you go up, what happened here? See here. What happened in this case? Just come here. In this case, we not subtracted. But if you will move up to this one, so see here. In this case, V1 added, V0 added, right? So either V0 will be add or subtract. Similarly, Vs will also add or subtract. Getting my points? Similarly, V0 will also add or Similarly, V0 will also add or subtract, right? So see, right now Vs 0, V0 0. So F apparent will be in this case. F apparent will be in this case, my dear, N0, because this becomes 0, this becomes 0, CC get cancelled, so this becomes N0. Go and see first case. I said that apparent frequency is equal to real frequency. If you will take case 2, I said source is moving towards the observer, right? Vs, and sound is also moving in the same direction. So relative speed of sound with respect to source, this will be C minus Vs. But V0, observer is at rest, so V0 will be 0. So apparent frequency will be N0 times C plus minus 0 by this becomes C minus Vs. Go and see, we have got this same result. So I'm not going to verify one by one. From these two cases, you can observe this formula is applicable for all cases. Then buddy, yes or no? Is there any issue? I think there should not be any issue. So right now I'm stopping my lecture here. The remaining lecture I uploaded soon, right? So till now, take care and good luck. Do your best, my dear students. Thank you everybody. Thanks everybody.